Hi, and welcome everyone to this partner webinar with Nowi. Today we're going to talk about how to power your cellular IoT product with the solar energy harvesting. So we are going to look at today's host first. It's me, Martin Lesund. I'm a technical marketing manager for cellular IoT, and I work for Nordic Semiconductor. And today we also have two people from Nowi. Please introduce yourself.
Hi, Chris Giuliano. I'm the Chief Commercial Officer for Nowi here in the Netherlands.
And I'm Karim Kilic. I'm an application engineer for Nowi in the Netherlands.
Just some practicalities before we start. The duration of this presentation will be around 30 minutes, and then at the end we will have a Q&A session. So questions are encouraged, and please use the question bar at the top right sidebar. All questions are anonymous, but to try to keep them relevant to the topic in this webinar. We will, of course, answer these questions at the end of the webinar. The chat is not anonymous and should not be used for questions. So if you have any questions after this webinar, you can go to DevZone for Nordic-related questions or to the NowieNRG.com contact for questions directed to the Nowi team. And a recording of this webinar will be shared after this presentation. So let's just go ahead and give Chris the word.
Okay, thanks, Martin. Appreciate inviting us today to talk about our product in the application of the Nordic modem within our energy harvesting Blue Coral board, as we call it. So just a quick agenda, little introduction about who Nowi is, high level overview of energy harvesting. Our NH2 is the chipset. But the majority of the presentation will be technical. Karim will be walking through all the details about how it works, how it performs, measurements of power and performance. We can talk a little bit about how to get started with the board. And as Martin was saying at the end, questions. And we already have a lot of questions coming in. We haven't even started yet. So let's get going. So Nowi, as we mentioned, based in Delft, Netherlands, which is famous for flowers and blue porcelain, but also Nowi. So we're a team of about more than 30 people. It's a new company with a focus exclusively on energy harvesting power management. We're not a spin-out, but the university at Technical University Delft is nearby. We have quite a few members of the team that came out of the lab there that's been doing research for more than 15 years on energy harvesting. There's no commercial relationship between the university and ourselves. We're a privately funded company. And by the way, Nowi means no wires. So the chip, which you can see on the right-hand side on our initial, actually that's our first development kit, sits in the middle of the process. The left-hand side are the energy sources, solar, RF, kinetic, thermal, and then you need, of course, a harvester, and we convert. So we're a boosting converter, inductorless system. And our goal is charging a storage device. Typically, in most commercial applications, it's a rechargeable battery, can be a supercapacitor. And the whole rationale for the chip, of course, is supporting the load. In this case, it's a sensor or sensors and the Nordic NRF modem. So the four primary features, unique aspects of our chip, which is a 3x3 millimeter QFN, currently that's how it's packaged, is the fact that it's inductorless. It's a patented design, and it needs only one very, very small external capacitor. So the footprint is typically 20 or 30 times smaller on a PCB design than from other energy harvesting chips. We also have a very, very fast MPPT that samples every second. And all this together leads to a very simple implementation and effectively a very low cost implementation. Today we're talking about a board that has a lot of stuff going on. But we also implement this with Bluetooth in things like watches or wearables, TV remote controls, shelf labels in supermarkets and things like that. So I will just hand it over from here. As I said, Kareem will walk through all the details.
Yeah, thanks, Chris. So just to talk a little bit about the simplicity and implementation in your design or your PCB or product, we have an example PCB layout on this slide, which is configured for outdoor solar harvesting. So as Chris already mentioned, we have there's only one external capacitor, which you can see it's located on the top right here, capacitor C1. Then there's the NH2 PMIC ICU1. There are only very few connections you need to make. So there are several connections to ground, which are shown here, pins connected to the outer ground plane. And for solar harvesting, there are several pins you need to connect, for instance, to the battery voltage, which you can see in this PCB layout with the two traces right here. And then really all you need to do on a PCB or design level is to route the harvester or the DC input of the PMIC to the harvester. And then the output of the PMIC simply route to the battery. And then you can simply start charging or implementing energy harvesting in your product or design. But we go a little bit in more detail. In this slide, I'll be showing the configuration of the NH2. So as Chris already mentioned, typically you have a harvester and a storage in your design. So as you can see, for outdoor solar harvesting, you would obviously have the solar cell, and then typically it has a decoupling capacitor, as well as the storage unit also has a decoupling capacitor, as you can see. So we're using lithium polymer-based battery chemistry. And then if you look more closely in detail to the PMIC, so it's already said it's a 16-pin PMIC. There are only very few connections you need to make. So there are some connections you make to ground. And then we have our one external capacitor, which is located right here for the voltage reference. The PMIC itself can be configured for both outdoor as well as indoor solar harvesting. We'll be mostly talking about outdoor solar harvesting in this webinar. So the configurations can be made with the range pins, which are shown right here, R0, R1, and R2, as well as the PWRS pin. So by setting these pins to the battery voltage, we configure the chip to work better in an outdoor application, outdoor solar application. But if we would like to use it, for instance, indoor solar harvesting, we could simply connect these to ground, and then the PMIC would be configured or optimized better for indoor solar harvesting. Other than that, there is an enable pin, which is located right here. By using the enable pin, you can effectively implement overcharge protection in your design. So by toggling the enable pin, which is an active low pin, you can simply enable or disable conversion. And by disabling conversion, once the battery voltage passes a certain threshold, you'll effectively implement overcharge protection. Some other maybe things to mention here. As Chris already mentioned, the PMIC is a boost PMIC, so it boosts by 2 or 2.3 times, or boosts the input by 2 or 2.3 times. So now I'll be explaining a little bit more about the Nowi Blue Coral board and how you can use it to develop for any autonomous sensor application based on Nordic Semiconductor's NRF91 SiP, as well as Nowi's NH2 energy harvesting PMIC. So really, in a nutshell, it is a development board or development platform for energy autonomous IoT sensors connected by cellular communication protocols. It uses nRF91 SiP, and then for the energy harvesting, it uses NH2 energy harvesting PMIC by Nowi. There is a microbus modular socket, which allows over 200 plus off-the-shelf available sensor add-on boards to be used in your development. And also one other key feature is that it also has a MFF2 footprint or an eSIM footprint. So you can also use eSIM or develop for any eSIM type of application. That's more the higher level. So now we're going a little bit more detailed description of the hardware. So as I already mentioned, there is a nRF91 SiP, which is located on the right-hand side of the board. And then there is in the middle of the board, we have a serial wire debugging interface, SWT interface, which is there to flash or provide the modem with firmware, application firmware or modem firmware. As well as on the right-hand side, we have an additional UART interface. So this UART interface, that's actually if you would flash the device with, for instance, Nordic's asset tracker example code or the AT client code, the logging for the UART will be selected to this channel here. So if you would be updating the NRF cloud certificate or something like that, you would be using this UART, this unpopulated UART channel right here. The board has an antenna with a fixed matching network. So the antenna supports both LTE-M as well as NB-IoT connectivity. And it has a fixed matching network, which means that you don't need to switch between different matching networks for different frequency bands. It supports the fixed matching network supports a majority of the frequency bands for LTE-M as well as NB-IoT. And then on the top here, we have a current measurement interface where you can measure both the VDD as well as the VDD GPIO for the nRF91 SiP, which you can use to power profile your application or to optimize your application for your nRF91. We will be showing a demonstration on how to use this interface to measure the currents in a video later in this presentation as well. And then there is a SIM switch on the left-hand side. So the board supports both eSIM as well as regular nano SIM, which you can see here on the bottom side. We have a nano SIM connector as well as an eSIM footprint. And by switching this SIM, you can basically select if you want to go for nano SIM or eSIM in your development. So as I already mentioned, it's for energy autonomous sensors. It supports NH2 energy harvesting PMIC, which is located in this silk screen box right here. And the board supports lithium polymer lithium polymer chemistry batteries, which you can simply attach by this 3-pin Molex connector, which supports lithium polymer batteries. There are 2 PV expansion board headers. So to connect a PV expansion board, which we'll be demonstrating in the video as well. The top left corner right here is electrically connected to the PMIC. So that's where the current from the PV will be flowing into the PMIC. And then the bottom right corner is there for mechanical stability. We will be showing this in a video demonstration later as well. And then there is a current measurement interface for the NH2 as well. So you can measure the battery charging current as well as the current flowing from the PV cell into the PMIC. And yeah, by measuring the battery charging current, you can determine if you need a bigger PV size or what type of PV you need to compensate for the consumption of this nRF91 module. And to power profile your solar harvesting currents. So as I already mentioned, there is a microbus socket, which is a modular embedded development standard, which we incorporate in the board right there. It supports over 200 plus as well analog as well as digital sensors, sensor clickboards. So I'm now going through some of the peripherals that are routed to that socket to give you an idea of the functionalities. There is an analog compatible pin in case you're using an analog clickboard. There is a analog channel of the nRF91 routed to the AN, the pin that's marked AN. There is a microbus device reset, which is routed to a GPIO of the NRF91, which in some microbus clickboards can be used to reset the microbus device by simply toggling that reset. There is a serial peripheral interface routed there with the chip select, the clock, master in, slave out, master out, slave in, which is a very common communication protocol for digital sensors, as well as for ADCs that you would use for analog-based sensors. And then we have a 3.3 volt power supply for the clickboard, as well as the current measurement interface. So by using that current measurement interface, you can power profile your sensor and then optimize the power consumption of your sensor. So for instance, for digital sensors, the power consumption would be, for instance, determined by sampling frequency. So you could measure the current of your sensor or the power supply current of your sensor right there, and then optimize the power consumption for your application. So on the right side, we have a pulse width modulation compatible pin. There is an interrupt compatible pin in case your sensor or your microbus slave device should generate an interrupt to the NRF91. There's another UART channel exposed right there for communication. There is an I2C or two-wire interface routed there, which is also a very commonly used communication protocol for digital sensors. The board has pull-up resistors on the right-hand side right here. So all that you need to do for an I2C based sensor is to simply click your sensor clickboard in the socket, and then you can start sampling your sensor. The board also supports a 5-volt power supply, which is normally disabled since most digital sensors use 3.3 volt. However, to comply with the design standard of microbus, that 5 volt is present there. You can enable it by soldering the jumper on the bottom side of the board. So normally this jumper would be soldered to R102, which would disable this regulator to decrease the overall power consumption of the board. However, if you want to use 5 volt in your design, you can simply move the jumper from R102 to R101, as shown here. So now we will be showing a video demonstration on how to use the board and how you can measure the currents, the solar PV current or the battery charging current, as well as the how to power profile the NRF91. Hello everyone, my name is Kareem. I'm an application engineer at Nowi. In this video, I will be demonstrating the Blue Coral development board and how to measure currents. I'm currently in an outdoor environment, as you can see. It's a pretty sunny day. I've measured the illuminance with my spectrometer, which is approximately 104,000 lux. We will now move on to the video. We will now show a demonstration of how to measure the battery charging current using the Nowi Blue Coral development board. We have a lithium polymer based battery and a PV expansion board with the Panasonic AM5308 PV. We have disabled the NRF91 by removing the current jumpers, and by simply removing the current jumper for the battery charging current, we can attach a measurement tool and start measuring the battery charging current. In this video, we will be attaching a DC energy analyzer. We attach the input of the DC energy analyzer to the plus side and the output of the DC energy analyzer we will attach to the minus sign. We will connect the ground of the DC energy analyzer to one of the exposed ground pads. And then we will attach the lithium polymer based battery in the 3-pin connector that's located right there. After all these connections are made, all we simply need to do is to attach the PV expansion board and then we can start measuring the battery charging current. As I already mentioned, the luminance is approximately 104,000 lux. So right now we are showing the battery charging current. As you can see, the battery charging current is slightly larger than 200 microamp. And each peak that goes downwards corresponds to the maximum power point tracker interval. In this demonstration, the battery charging current is approximately 240 microamp. And you see that the battery voltage is 3.75 volt and is rising due to the battery being charged. We can also measure the input current of the PMIC. We were just measuring the output current of the PMIC, the battery charging current. We can remove the PV expansion board. And then all we need to do is simply to move the measurement tool from the output of the PMIC, located right there, to the input of the PMIC. We connect the input of the DC energy analyzer to the plus. And we connect the output of the DC energy analyzer to the minus sign. After switching from the output to the input, we can simply reattach the PV expansion board to measure the input current of the PMIC. Now we are showing the input current measurement of the PMIC. As you can see, the current is equal to slightly larger than 600 microamp. And again, each downwards peak in the current and power correspond to the maximum power point tracker interval. And the voltage of the PV is approximately 2.5 volt. Similarly, the peaks upwards with the PV voltage also correspond to the maximum power point tracker interval. We will now show a demonstration on how to power profile the nRF91. So we will simply disconnect the PV expansion board and also disconnect the DC energy analyzer and reconnect our current jumper. In this demonstration, we will be showing the asset tracker example code provided by Nordic Semiconductor. So the first thing that we need to do is we need to attach a SIM card to the board. In this demonstration, we will be using an iBasis nano SIM card, which will be attaching in the SIM holder located on the bottom side of the PCB. After attaching the SIM card, we need to set the SIM switch to SIM so that the SIM is selected instead of the eSIM. We will reattach the lithium polymer battery. And then we can connect our measurement tool to the nRF91 current jumper. We will be connecting the input of the DC energy analyzer to the plus sign and the output of the DC energy analyzer to the minus sign. We'll be connecting the ground of the DC energy analyzer to one of the exposed ground pads. then we will reattach the PV expansion board and start our measurement. Right now we are measuring the current and the power of the NRF91 SiP. And you can see some of the peaks and the idle current. By using the current measurement capability, you can power profile your application and optimize the power consumption in order for your application to become energy autonomous. Right now we are running the asset tracker example code provided by Nordic Semiconductor. By selecting a suitable PV panel, as well as a suitable battery, you can make your application energy autonomous with the Blue Coral development platform. So far a demonstration of how we can use the board and what the, let's say, power profiling capabilities of the board. So as I showed in the video demonstration, the battery charging current for a regular Dutch outdoor environment is approximately 240 microamp at 3.7 volt. So now just to give you an idea what type of applications would be possible, we have some average consumption values based off the Nordic online power profiler tool. So there we have selected the second revision of the NRF91 SiP. We're using LTE-M communication in PSM, in power saving mode. And the message interval would be 1 hour. So every hour we would be sending a message with a payload of approximately 1 kilobyte. So as you can see in this table here, the consumption varies between, let's say, 24 microamp for the US, maybe to 43 microamp for Norway. And yes, I already mentioned, so in the video we show a battery charging current of approximately 240 microamp, which would mean that in these geographical locations, it would be possible to have an energy autonomous asset tracker, or you could add some extra electronics there, since there is some headroom. Let's say you have some 200 microamp headroom, so you could add extra sensors there, or you could simply use the same type of PV and increase the message interval or the message payload. And yeah, the application would still be energy autonomous. And I'll be giving the word back to Chris.
Okay, thank you. Yeah, possible applications, as I think the audience knows, asset tracking, wireless sensors, smart city, agriculture, anywhere where you want broadcasting data using cellular modem. So getting started, the board, it will be available sometime between 4 and 8 weeks from now. It's a little vague. I apologize, as I think everyone's been hearing. Our chip's available, but componentry's been a little bit slow, but we expect that. So for the US, it will be on DigiKey. I'm not sure about Canada, but for US. For any other market, or actually for any questions beyond just going on your own and getting it from DigiKey, feel free to reach out to us. We can discuss in a lot more detail any applications that you're looking at, and also I'm already seeing some questions about the reference design, and the documentation and the files will be available for the reference design itself as well.